Hello and welcome back. In the last video, I talked about the physical properties of haloalkanes and haloarenes. Then we looked at some examples of polyhalogen compounds that are used widely in our day-to-day lives. In this video, we will be discussing about some reactions of haloalkanes and I will be talking about reactions of haloarenes in the upcoming videos. So let's get started. What are the main reactions that haloalkanes undergo? First one is nucleophilic substitution. Then we will look at elimination reactions and at last we will end with reaction with metals. So before jumping onto nucleophilic substitution, first of all, what is a nucleophile? If you have not heard about this term yet, don't worry, it is pretty simple. Nucleophile is nothing but a chemical species that donates a pair of electrons to form a chemical bond. Example F minus. So what is a nucleophilic substitution? Fairly obvious. In this type of reaction, a nucleophile reacts with haloalkane, that is a substrate, having a partial positive charge on the carbon atom bonded to halogen. A substitution reaction takes place and halogen atom called leaving group departs as halide ion. Since the substitution reaction is initiated by a nucleophile, it is called nucleophilic substitution reaction. Schematically, Rx plus Nu minus by Nu minus is nucleophile and Rx is the alkyl halide. When this reacts, we get RNu and halide ion. And since the halogen has left alkyl halide, we call it the leaving group. Next, we will look at some nucleophilic substitution reactions. That is, if we treat alkyl halide with a reagent, what is the substituted product that we get? And what exactly is the nucleophile in the reagent? First in the line is sodium hydroxide or equivalently potassium hydroxide. The nucleophile here is OH minus and we get alcohol, that is ROH. If we treat it with water, the water itself is a nucleophile and we again get ROH. When treated with NaOR, we get RO minus as nucleophile and we get an ether. When treated with KCN, we get CN minus as the nucleophile and the product is RCN. If it was with AgCN, then the nucleophile is AgCN and we get an RNC, that is an isocyanide. We will look into this nature of cyanide in the next slide. Let's go faster. With KNO2 we get RONO and with AgNO2 we get INO2. We will again look at this in the coming slide. Then with ammonia, the nucleophile is NH3 itself and we get INH2, that is a primary amine. Instead of ammonia we can have a primary amine. In that case we get a secondary amine, that is with RNH2 we will get RR-NH2, something like that. And if you treat it with a secondary amine, then the substituted product will be a tertiary amine. Next with R-COOAg, we get R-COOR, that's an ester. Notice that the bond here is formed between O and R and not with R and C. By the way, I have used R and R interchangeably, but with slides I think you will understand. Next, an important reducing agent, that is LiAlH4. The nucleophile is an hydride ion and we get RH, that is an alkane. And finally we have an RM, that is a bond with metal, and in such a case we get a long chain alkane. Now as I had promised, let's look at the nature of cyanide, which is again an ambident nucleophile. So what is an ambident nucleophile? Groups like cyanides and nitrites possess two nucleophilic centers and are called ambident nucleophiles. Actually, cyanide group is a hybrid of two contributing structures and therefore can act as a nucleophile in two different ways. That is, linking to a carbon atom results in alkyl cyanides and to nitrogen atoms we get isocyanides. Similar thing can be observed with nitrite ion. The linkage to oxygen results in alkyl nitrates, while to nitrogen atom it leads to nitroalkanes. So, or nucleophilic substitution reactions, that's simple. Or are there any mechanisms? Are there many types of nucleophilic substitution reaction? Let's look at that. Now we're going to see some mechanisms of nucleophilic substitution reaction. This reaction has found to proceed in two different mechanisms. Substitution nucleophilic bimolecular, which is known as SN2 reactions, and we have substitution nucleophilic unimolecular, that is SN1 reaction. Let's study about SN2 first, then we will move on to SN1. So SN2 reactions follow second order kinetics, that is, the rate of the reaction depends upon the concentration of both the reactants. An example of such a reaction is the reaction between CH3Cl and OH minus ions, which gives CH3OH and Cl minus ion. Now let's look at the reaction mechanism. We have an alkyl halide, and when this is treated with a nucleophile attacks the carbon, and now the carbon holds 5 groups. It is something like pentavalent, and this state is unstable. By the way, the condition is called transition state. To complete the reaction, the halogen leaves as halide ion and gives the desired product. The product is said to be inverted, and we will look at this term inverted in the next video, where I will be talking about the stereochemical aspects of a nucleophilic substitution reaction, in more generally any reaction. The incoming nucleophile interacts with alkyl halide, causing the CX bond to break while forming a new COH bond. These two processes take place simultaneously in a single step, and no intermediate is formed. As the reaction progresses and a bond between the nucleophile and the carbon atom starts forming, the bond between the carbon atom and the leaving group weakens. As this happens, the configuration of carbon atom under attack inverts while the leaving group is pushed away, and this process is known as inversion of configuration. Don't worry about this term, I will be talking about this in detail in the next video. In the transition state, the carbon atom is simultaneously bonded to incoming nucleophile and outgoing leaving group. Such structures are unstable and cannot be isolated because the carbon atom in the transition state is simultaneously bonded to 5 atoms. So this was the summary of the reaction mechanism. Since this reaction requires approach of a nucleophile to the carbon bearing the leaving group, the presence of bulky substituents on or near the carbon atom have a dramatic inhibiting effect. Of the simple alkyl halides, methyl halides react most rapidly in SN2 reactions because there are only 3 small hydrogen atoms. And as you might have guessed, tertiary halides are the least reactive because of the bulky groups that hinder the approaching of nucleophiles. Thus, the order of reactivity followed is primary halide first, then secondary halide, and the least reactive or the tertiary halides. Now let's move our discussion to SN1 reaction. SN1 reactions are generally carried out in polar protic solvents like water, alcohol, acetic acid, etc. The reaction follows the first order kinetics, that is, the rate of reaction depends upon the concentration of only one reactant. Example, the reaction between tertiary butyl bromide and OH minus ions yields tertiary butyl alcohol. The rate depends only on the substrate, that is tertiary butyl bromide here. We have the reaction CH3 thrice CBr plus OH minus gives CH3 thrice COH, that is alcohol that we need, plus Br minus. This SN1 reactions occur in 2 steps, unlike SN2 reactions that occur in 1 step. So what are the 2 steps? The first step is the polarized CBr bond undergoes slow cleavage to produce a carbocation and a bromide ion. So this SN1 reactions form an intermediate, that is a carbocation intermediate. The second step is that the carbocation thus formed is then attacked by nucleophile to complete the substitution reaction. In the first step, there is CH3 thrice CBr and it forms a carbocation by cleavage of C-Br bond. And in the second step, the Wurtz minus attacks the intermediate, that is a carbocation intermediate, and it forms the desired product, that is tertiary butyl alcohol. Step 1 is the slowest and reversible. It involves the C-Br bond breaking, for which the energy is obtained through solvation of halide ion with the proton of protic solvent. That's why we need a protic solvent. Since the rate of reaction depends upon the slowest step, the rate of the reaction depends only on the concentration of alkyl halide and not on the concentration of hydroxide ion. That's the reason why it follows first order kinetics, and the rate does not depend on the concentration of hydroxide ion. Further, greater the stability of carbocation, greater will be its ease of formation from alkyl halide and faster will be the rate of reaction. So one point to note here is that in SN2 reactions, bulkier groups hinder the rate of reaction, and hence we prefer primary more than secondary and least is tertiary. However, in SN1 reaction, the tertiary carbocations are most stable, and hence tertiary alkyl halides are most reactive, while the primary alkyl halides are the least reactive. So let me put what I have said in the video. In case of alkyl halides, tertiary alkyl halide undergo SN1 reactions very fast because of high stability of tertiary carbocations. So the chart that we have is an alkyl halide, that is tertiary, secondary, primary, and methyl halide. For SN2 reactions, the stability increases from left to right. That is, tertiary alkyl halides are the least reactive, while methyl halide is the most. And as expected, for SN1 reaction, it's the reverse. That is, the tertiary alkyl halides are the most reactive, while the primary and methyl halides are the least reactive ones. For the same reasons, allylic and benzylic halides show high reactivity towards SN1 reaction because of stabilization by resonance. So we have an alkyl halide over here. We have an allylic halide over here, and this can happen. The pi electrons can shift, giving rise to this structure, and again, due to resonance, we get back the first structure. So we have a canonical structure like this. Similarly, you can draw resonating structures for benzylic halides, and because of resonance, the carbocation is stabilized. For a given alkyl group, the reactivity of halide Rx follows the same order in both the mechanisms. That is, Ri is most reactive and Rf is the least reactive. So let's try to solve some questions. Haloalkanes react with KCN to form alkyl cyanides as main product, while AgCN forms isocyanide as the chief product. You might have seen this in the previous slide where I showed you the table of reagents and substituted products, and you might be wondering why. So let's give it a shot. You can pause the video if you want more time to think, but I will be proceeding in another 5 seconds. So yeah, let's look at the solution. KCN is predominantly ionic and provides cyanide ions in solution. Although both carbon and nitrogen atoms are in a position to donate electron pairs, the attack takes place mainly to carbon atom and not to nitrogen atom, since CC bond is more stable than CN bond. However, in case of AgCN, AgCN is mainly covalent in nature, and nitrogen is free to donate electron pair, forming isocyanide as the main product. So now I think you would be clear why KCN formed cyanide while AgCN formed isocyanide. And a similar explanation can be given for the other case also, that is where we had KNO2 and AgNO2. Let's look at another example. Let's try to predict the order of reactivity of the following compounds in SN1 and SN2 reactions. First one in the line is the 4 isomeric bromobutanes. So let's look at the answer first. So this is the answer, and let me give you the explanation now. Of the two primary bromides, the carbocation intermediate derived from CH3 twice CH2Br is more stable than that derived from CH3CH2CH2CH2Br because of greater electron donating inductive effect of CH3 twice CH group. Therefore, CH3 twice CH2Br is more reactive than CH3CH2CH2CH2Br in SN1 reaction. CH3 twice CH2 CHBr CH3 is a secondary bromide and CH3 twice CBr is a tertiary bromide. Hence, the above order is followed in SN1. The reactivity in SN2 reactions follow the reverse order as steric hindrance around the electrophilic carbon increases in that order. And please note that it's not always the case that SN2 is the reverse of SN1. For SN2, you have to look at the steric effects, and SN1, you have to look at carbocation stability. It's not the reverse all the time. Let's look at another example. Let's try to predict the reactivity of the following compounds. Okay, let's look at the solution now. We have the answer first. So this is the order for SN1 in the first line and SN2 is in the second line. Now let's look at the explanation. Of the two secondary bromides, the carbocation intermediate obtained from C6H5CH C6H5Br is more stable than that obtained from C6H5CH3Br because it is stabilized by two phenyl groups due to resonance. And I would like to tell something here. Resonance is more stabilizing factor than inductive effect. That is, if you have resonance and inductive effect, resonance stabilizes a carbocation more than an inductive effect. And obviously, you have to look at which resonance it is, either it is plus R or minus R. And yeah, if you have a fight between resonance and inductive effect, this is the point. Resonance wins. So, therefore, the former bromide is more reactive than the latter in SN1 reactions. A phenyl group is bulkier than a methyl group. Therefore, C6H5Br is less reactive than the other one in SN2 reactions. Hope these two questions are clear. And we have come to the end of nucleophilic substitution reaction. In the book, there is a part 4.C, I suppose, which talks about stereochemical aspects of nucleophilic substitution reaction. I would like to discuss that concept in a separate video in good detail, so don't forget to watch the next video. Now we will be talking about elimination reactions. As the name says, in elimination reaction, something is eliminated, which you would have seen in the previous classes also, that is in class 11. So when a haloalkane with beta hydrogen, what is beta hydrogen? A hydrogen at beta position, what is beta position? A second carbon from the carbon to which the halogen is attached. So that is a beta hydrogen atom. So when a haloalkane with beta hydrogen atom is heated with alcoholic solution of potassium hydroxide, there is elimination of hydrogen atom from beta carbon and a halogen atom from the alpha carbon atom. What is alpha carbon atom? similar explanation. It is the same carbon to which the halogen was or is bonded. And note that here the reagent is alcoholic solution of potassium hydroxide. In the nucleophilic substitution reaction, it was aqueous solution. Aqueous solution gives OH minus as the reagent, and in alcoholic solution we have RO minus as the ionic species. So as a result, an alkene is formed. Since beta hydrogen atom is involved in elimination, it is often called beta elimination. So as you see here, we have a halogen bonded to a carbon, and that is to the right, and the carbon that is to the left of that carbon, there's a hydrogen. So that carbon is called beta carbon. And we have a B minus. What is B minus? B minus is a base. And what is X? X is called a leaving group as usual. So now this base comes and attacks the beta hydrogen and extracts it, forming a pi bond, and then the halogen is expelled as halide ion. So we get an alkene with some byproducts. So the B is base and X is leaving group. If there is possibility of formation of more than one alkene due to availability of more than one beta hydrogen atoms, usually one alkene is formed as a major product. And this is given by something called a Sage-Off rule, which states that in dehydrohalogenation reactions, by the way, dehydrohalogenation because a hydrogen is removed and a halogen is removed, and hence the name dehydrohalogenation. So in dehydrohalogenation reaction, the preferred product is that alkene which has the greater number of alkyl groups attached to the doubly bonded carbon atoms. So let's look at this with an example. We have 2 bromopentane in the middle, and we make it undergo beta elimination. So we get two products, one on my left and one on the right of the screen, and we observe that 2-bromopentane gives 2-pentene as the major product. So the double bond is formed between the formed where there are greater number of alkyl groups, that is less number of hydrogen. So a double bond is formed between the second and third carbon instead of first and second carbon. So now we were looking at substitution and elimination. We observed that both compete with each other. In that case, how do we know if the given reagent and the given reactant will undergo elimination or substitution? A chemical reaction is result of competition. A collection of molecules tend to do by and large what is easier for them. An alkyl halide with beta hydrogen atoms, when reacted with a base or a nucleophile, has two competing routes: substitution SN1 and SN2 or elimination. Observe that a nucleophile is also a base and a base is also a nucleophile. Which route will be taken up depends upon the nature of alkyl halide, strength and size of base or nucleophile, and the reaction conditions. Thus, a bulkier nucleophile will prefer to act as a base and abstracts a proton rather than approach a tetravalent carbon atom, and vice versa. This is because of steric reasons. So, which means if we have a bulkier base, it tries to act as a base and abstracts a proton and leads to elimination instead of substitution. Similarly, a primary alkyl halide will prefer a SN2 reaction, which we have seen before, and a secondary halide, SN2 or elimination, depends upon the strength of base or nucleophile. A tertiary halide, SN1 or elimination, depending upon the stability of carbocation or more substituted alkene. So let's look at the last concept of this video, that is reaction of haloalkanes with metals. Most organic chlorides, bromides and iodides react with certain metals to give compounds containing carbon-metal bond. known as organometallic compounds. So what is organometallic compounds? A compound that has a carbon-metal bond. An important class of organometallic compounds discovered by Victor Grignard in 1900 is alkyl magnesium halide, that is RMGX, referred as Grignard reagents. These reagents are obtained by reaction of haloalkanes with magnesium metal in dry ether. So we have an alkyl halide RBr and we treat it with Mg in presence of dry ether, we get RMgBr. So why do we need a dry ether? In Grignard reagent, the carbon-magnesium bond is covalent but highly polar, with carbon pulling electrons from electropositive magnesium. The magnesium halogen bond is essentially ionic. So my question is still open. Why do we need a dry ether? Grignard reagents are highly reactive and react with any source of proton to give hydrocarbons. Even water, alcohols, amines are sufficiently acidic to convert them to respective hydrocarbons. So if we have RMGX, in presence of water we get RH, that is an alkane, and byproduct MgOHX. So that's why we use dry ether instead of water or aqueous conditions. It is therefore necessary to avoid even traces of moisture from Grignard reagent. On the other hand, this could be considered as one of the methods for converting halides to hydrocarbons. So it depends on what we need to do. If we need to get an alkane, then we make it react with water after the Grignard reagent is formed to get higher order alkanes. If we need to preserve it, we need to avoid its contact with moisture or in fact with any source of proton, including water, alcohols, amines, etc. So another class of reactions that comes under reaction of haloalkanes with metals is Wurtz reaction. This is the last reaction that we are going to see. And alkyl halides react with sodium in dry ether to give hydrocarbons containing double the number of carbon atoms present in the halide. This reaction is known as Wurtz reaction that we have seen earlier. And 2 moles of RX with sodium in dry ether, we get RR, that is an alkane with 2 moles of NaX as byproduct. So what we have achieved here is that we have got a hydrocarbon, an alkane, from alkyl halide, and this hydrocarbon has the double the number of carbons that were there initially in the alkyl halide. With this, I would like to conclude this video. To summarize, we learnt about the chemical reactions of haloalkanes. We started off with substitution reactions, which included SN1 and SN2 reactions. Then we looked into elimination reaction, specifically dehydrohalogenation. Then we saw who wins among substitution and elimination. And finally, we saw reaction of haloalkanes with metals, which included the Grignard reagent and Wurtz reaction. In the next video, I would like to talk about the stereochemical aspects of substitution reaction, and the video following that, I would like to talk about reactions of haloarenes. So, I hope this video was clear and hope to see you in the next video. Goodbye.